Hi everybody, my name's Tom Wilson. I'm an Associate Professor of Disaster Risk and Resilience at the University of Canterbury. I'm going to be talking today a little bit about the science around the Alpine fault, and it's part of the AF8 initiative, which is looking at planning for a future Alpine fault event and how we might reduce some of the potential impacts of an event like that. So I'm part of a great big scientific team, and I'm presenting on behalf of them a lot of the science that's been produced over the last couple of decades. And particularly over the last 5 years, which provides us a really world-class resource for looking at what a future event might look like. So what I'm going to talk about is what do natural hazard scientists worry about when we're thinking about a future big earthquake event. So the first thing that we need to know about is what is the magnitude of the event going to be. So how big is that event going to be in terms of the amount of energy or the volume that might be produced. So in the case of big earthquakes, we're interested in how much power or how much energy is released during an earthquake. The next thing we're interested in is what's the frequency? How often do these events occur? So you can also call that what's the likelihood of it occurring. And really, I guess what we're interested in is what's the personality of the fault system, how often does it rupture, and when might we be able to forecast if that event is going to occur. The next thing that we start to think about, which starts to get a little bit sciencey, is what we call the hazard footprint. And really what we're talking about there is what is the area that might be affected in a future disaster. So we can also call that the spatial extent. So how much area is going to experience ground shaking from a future Alpine fault event? And then we break that down into thinking about what is the intensity that we might experience at this location or a variety of locations. We describe that as saying, how long or strong might the effects of that hazard event be in space and in time? So what is going to be the duration of shaking that we experience here in Christchurch where we're recording this video? The other things I'm going to talk a little bit about is some of the potential consequences that we might experience from an event like this. So starting to think about what might be the impacts which can occur, which leads us to how we might start to reduce what those consequences could be. Okay, so we'll start out with looking at what the magnitude of this potential event might be. So when we're thinking about the Alpine fault, from a scientific point of view, it is one of the absolute classic strike-slip faults that we have for a plate boundary fault system on Earth. So when we're looking at this, we can see this image here, looking at the long view of the South Island. And what you can see running along that very straight lineation on the western side of the Southern Alps, what you're seeing there is the Alpine fault. And this other image that we're looking at the right-hand side is looking along the strike of the fault. So what we can see is we're looking from the south, looking north along the Southern Alps, up towards through Marlborough and Nelson, and towards the southern part of the North Island. And you can just see Wellington in the distance there. What we're looking at is the Alpine fault, and it's around about 400 kilometres in length. Now the reason that we know that it's a fault line is we can go up and have a look at the area and see where that lineation might be in the ground. But the key thing from a geological point of view is that the rocks that we see down here in Western Otago and Southland are actually the same as what we have up in northwest Nelson. And that fault line over millions of years has displaced them. And as it ruptures away over a number of probably hundreds to thousands of events. So it's a very mature fault system. Now, the thing that we're most interested in terms of calculating how big is this future event going to be is we need to know what the length of the fault will be, and that can give us an indication of how much energy might be released. So the way to think of it is if you put your two hands together and press them really tight, and if you've got really long hands, or the longer your hands and the more surface area that you have between them, and as you're trying to pull them apart like that, you'll start to feel energy being produced. It's a bit of a cold day here. I've got slightly cold hands. I'm actually quite enjoying doing this. It's providing a bit of warmth. But what you're effectively producing is you're having that energy being released as your hands move past each other. Now that's the same thing that's happening with the Alpine fault, where we have the Pacific and the Australian plate basically grinding against each other. Now they're not moving in a nice smooth motion like what my hands are doing there. They're actually locked together, really tightly compressed, and when they rupture in breaks, and energy is released quite quickly. So if you've got your hands together, pressed really tight, and you give it a quick sharp rupture, you'll feel much more energy and warmth be produced. What you're kind of producing is seismic energy or seismic waves. and those waves will radiate out and lead to the earthquake being produced. So when we're coming back to the Alpine fault situation, we're interested in how long that fault might be and how deep that fault extends down into the earth. So with that very long distance of 400 kilometres, that can lead to potentially a magnitude 8.1 earthquake, which is a very, very large earthquake, and starts to get our attentions as geoscientists. I'll explain a little bit more about what that might potentially mean. Now, what we're interested in is, does that fault rupture the full length of the fault line or not? So it's an important question that we need to ask. Now, some of the wonderful work that's been done by GNS Science, along with a number of others from the University of Otago, Victoria University Wellington, University of Canterbury, and a number of others from all around the world, have been actively studying this fault for decades, and there's been some tremendous work. And I'd say in many ways it's probably one of the most well-studied faults on Earth, so we're very fortunate to have that wonderful scientific legacy. What we're looking at when we have an earthquake like that is that when the fault goes into a rupture, or starts to rupture along those lines, the fault probably has enough stored energy to move up to over 8 metres horizontally, especially in the central segment of the fault, and potentially up to 2 metres vertically. So think about what that might mean with your hands together, and as you're moving them, there's a huge amount of distance that's moved during that event, and imagine all the energy that's required to move the fault line over that distance. Now, there'll be more motion in the central part of where that fault line has moved. At the tips, there'll probably be only quite a small amount of movement, but nevertheless, a huge amount of energy will be released in that event. Now, it's very important to remember that magnitude scale, when we're talking about earthquake magnitude, is an exponential one. When we're thinking about recent big earthquakes that we've had here in New Zealand or here in Canterbury, is we had the 4th of September 2010 Darfield earthquake, which was a magnitude 7.1. So when we compare that to a magnitude 8 earthquake on the Alpine fault, the Alpine fault earthquake will have 32 times more energy being released than occurred in the Darfield earthquake. When we relate that to the 22nd of February 2011 Christchurch earthquake, it's well over 1,000 times more energy would be released in an Alpine fault earthquake. So it's important to keep those sort of orders of magnitude scales in mind when we're thinking about how much energy might be released. So instead of, with the Darfield earthquake, it was really a big regional event which occurred. With Christchurch earthquake, it was, a lot of those impacts were constrained largely to the Christchurch urban environment. With an Alpine fault earthquake, we're likely to see a South Island-wide event being produced. Okay, so the next thing we need to be thinking about is the frequency, or what's the likelihood of the next event? Or when, and ideally, if we can forecast, when is that event next going to occur? Which in natural hazard science is very, very difficult to forecast. But what's wonderful about this fault, where it's been some incredible work done, especially by our GNS Science colleagues over the last 5 to 15 years, is they've been starting to unravel the number of different earthquakes that have occurred on that fault line. So some of the new research that's been undertaken by Ursula Cochrane and her team at GNS is looking down at the southern portion of the Alpine fault and starting to look at areas where the fault line has displaced different rivers or different sort of swampy type areas. And every time that you displace them, so that sometimes, if you're lucky enough, a little bit of carbon will be captured in that displacement. So it might be a case where the fault has moved and it's trapped a piece of wood or whatever, or peat, and it's locked up underneath some gravel or other sediment and sort of stabilised there. Or it might be that because of the sedimentary response, where new gravel or sand is laid down by a river or whatever, and it locks that carbon in place. If we look over time with the different earthquake events, is that we can start to date that carbon and start to look at when those events may have occurred. So what we're seeing with this plot that you can see here on the screen is that this team has managed to pick up over 27 different earthquakes on the Alpine fault over the last 8,000 years, which is just simply absolutely outstanding. It's difficult to emphasise how special this is as a scientific data set. So looking on this plot here, if we look on that x-axis up the top, we can see from 2000 AD, so that's the year 2000, and then we can move back in time, and we go all the way back to 6,000 years ago. And what you're seeing with those little wiggly things on the plot is the carbon date or the carbon age estimate that's been produced. So we use that as a dating technique to look at how old carbon might be from when it was deposited. So what you'll see there is a sort of a lumpy figure. What that's showing is the uncertainty of the age date. But the key thing I think here is to look at how regular the estimates of those ages are through time. And that tells us that the personality of this fault line seems to be that it ruptures quite regularly through time. Now we can start to look at some of the statistics around this, but the key take home is that it's a very regular occurrence through time. So the longest interval between different rupture events seems to be around about 510 years, and the shortest interval is 140 years. Now this might mean that different segments of the fault is rupturing or whatever, but the key take home is that there's very regular rupturing of this fault line through time, so we're having very regular earthquakes. So with this new data that's starting to come in, it seems that on average, and remembering it's on average, that the mean recurrence interval, or the how frequently on average it seems to rupture through time, seems to be about 300 years. Now, importantly, we've got quite a lot of evidence, and quite compelling evidence, that it appears the last earthquake was in 1717 AD. So that means it was about 300 years ago. So the key thing from that is we can probably start to take that this fault system is probably starting to get towards the end of its what we call the seismic cycle. So it's probably re-stressed up, and it doesn't mean that we're statistically overdue or anything like that. What it means is that every day that we go on without an earthquake on the Alpine fault, there's just a little bit higher probability that we'll have an earthquake in the future. Hence, it's a really good thing to be preparing for an event like this. Now, for those of you that are sort of statistically minded, what that probably means is that with this data, which is from the southern portion of the, or southern segment of the Alpine fault, that southwestern section, there's a conditional probability of around about 30% or 29% probability that the southwestern segment of the Alpine fault will rupture in the next 50 years. So a very compelling case that we should be preparing for an event like this in the future. Okay, so that's all good. So you might say, Tom, that's nice, all these statistics. What's it going to look like? So the thing that I like to visualise, because I'm quite a visual person, is what is it going to look like? What's the spatial extent, or what's that hazard footprint going to be? So the image that I'm showing you here is what we call an isosizemore map. So it's showing areas of where we think equal shaking will occur. So the image that you're seeing here is trying to provide an estimate of what the likely shaking intensity will be. So based on the scenario where there's a 400 kilometre long rupture of the Alpine fault, what would be the likely shaking that we would experience across the South Island? So what you can see here is as you're getting into this map, you can see there's different intensities, and we call them modified Mercalli intensities. What they are is sort of a qualitative measure of what the kind of the damage or the impacts or what we will experience as a society at these different areas. So what you can hopefully see from this image is that as we're close to the fault line, we've got quite high shaking intensities, so high intensities. So there we would be expecting quite a lot of potential damage to buildings, very strong shaking, probably a lot of landsliding, very disturbing for any person that's experiencing it. We're likely to seeing quite high, strong shake that's there. Now, as we think across to the Canterbury region, what hopefully you're starting to see is that it's what we call attenuating. So as we move further away from the fault line, the relative shaking intensity is decreasing. So it's a little bit like a good analogy, which is sometimes slightly overused, but I think a good analogy is a little bit like when you plop a stone into the middle of a big pond and the waves radiate out away from it. As they move away, they're becoming smaller and smaller and smaller. So that's that energy dissipating. It's the same sort of principle that we're seeing here. Now, what you hopefully can take from this image is that this looks like it's going to be a South Island-wide event. And it can be quite hard to sort of comprehend for me. So I find it useful to compare it against other earthquake events that I've experienced. So let's compare it at the same map scale to the Darfield earthquake from 2010, which much of Canterbury would have felt, and to the 2011 Christchurch earthquake. What you can see from these images is the same intensity scale projected at the same map scale. So the Darfield earthquake, it affected much of the Canterbury area, but as you can see, it's a much smaller footprint compared to the Alpine fault earthquake model. And we can see also with the Christchurch earthquake, again, much less energy was released. Unfortunately, it was right all underneath Christchurch, so very damaging, but really quite a small footprint affected by that earthquake event. So this just gives us a sense of the different sizes and scales that we might be experiencing here. Okay, so now what we're going to show is some amazing new work that's been led by Brendan Bradley and his team at the University of Canterbury. And what we're going to have a look at here is a ground motion simulation model. Now, what Brendan and his team have been able to produce is a physics-based model which is looking at how the ground motion might play out during an Alpine fault or a potential Alpine fault earthquake. So the image that you're seeing here as we press play is the fault rupture starting down at the southern portion of the Alpine fault. Now this is something to keep in mind, is that we don't know where that fault rupture might begin. It could be at the southern portion, could be at the northern portion, or it could start somewhere in the middle and radiate that way. But in this particular scenario, it's starting at the southern portion. And the reason we've chosen this scenario is it probably means slightly more shaking for Canterbury. So it's a good to sort of think about what those potential sort of higher end hazard could be. So, but what we're seeing here is as the fault rupture progresses, so it's moving along, that rupture is occurring along that 400 kilometres of the fault line, you're seeing the waves starting to radiate out as that energy is being released and the seismic waves are moving away. Now the problem is that the rupture speed is about the same as the speed that the earthquake waves radiate out away from that rupture source. So the great thing that this video is showing is seeing how that propagates through space and time. So as that video progresses, we're starting to see the waves moving through the hard bedrock of the Southern Alps, so nice hard material. Those waves are moving through quite quickly. But then as it starts to enter into the Canterbury area, especially down in the Canterbury Plains, we've got that nice, soft, unconsolidated sediment, that stuff that's been deposited by rivers and glaciers over relatively recent geological time. So they're quite unconsolidated. So what that's doing is it's actually amplifying the waves as they move through it. And you're seeing as the seismic energy enters into Canterbury, it's sloshing around in that basin. It's reflecting off different hard rock structures. And especially where we have really unconsolidated soils, it's continuing to propagate in those basins. So it actually means for this type of model gives us a very, very good view of what the potential shaking intensities that we might see in different locations throughout the South Island as it progresses. Now, if we continue that video and we see the energy continuing to move forward, or move northward, I should say, through Marlborough, Nelson, Northern Canterbury and so on, you're seeing that big wave front of energy that's all stacked up, moving forward, and so quite a lot of seismic shaking likely to occur in the north, and then also delivering into Wellington. So very similar to what we saw with the Kaikoura earthquake, where the rupture was quite directed towards the north, and Wellington received quite a large shake as a result. So that Kaikoura earthquake in 2016 is quite a good analogy for some of the impacts that we might see from an event like this. After that sort of spectacular video, and again, really want to acknowledge Brendan Bradley and his team that's produced a lot of that work. But what that gives us a good sense of is what those ground motions might be across the South Island. Now, earthquakes aren't all just about the ground shaking. One of the things that we're always really interested in is they tend to produce a series of what we can call secondary hazards or co-seismic hazards. So when we have nice, big, beautiful, steep terrain, shaking those big mountains can often lead to landsliding. Where we have the soft, unconsolidated sediments with lots of groundwater or saturated sediments, that can lead to liquefaction. So when we have a big earthquake like the Alpine fault with quite a high shaking intensity and particularly the long duration of shaking, what we're starting to see is the potential for quite severe secondary hazards or these co-seismic hazards. Now, the important thing to remember is that New Zealand has had decades of seismic risk reduction. So we've got very strong building codes, and many of our buildings and other critical infrastructure usually perform pretty well when exposed to ground shaking. And especially in Canterbury, where we've had a series of earthquakes or earthquake sequences, where a lot of our older buildings, which weren't built to those high standards have either been demolished or been retrofitted and strengthened. So in many ways, Canterbury is actually quite well placed for dealing with future big earthquakes. But the thing that we worry about is that often these secondary hazards, especially in high-income countries which have these high building codes and so on, they can be some of the most damaging and difficult to manage. And we've seen that play out with the Kaikoura-Huranui earthquake in 2016 and the challenges that produced. So we look at this list here on the screen. We've seen issues such as in Christchurch, where in many cases, most of our buildings and other built environment performed pretty well, with a few terrible exceptions, but mostly it was the liquefaction ground damage and rock falls which caused most of the problems, which hadn't been necessarily well planned for and caused a few surprises, and certainly led to a lot of economic loss and social and impacts as well. We look through, particularly I think in the case of the Alpine fault, a future Alpine fault earthquake, the Kaikoura earthquake from 2016 is a really good analogy of what might occur in those mountainous environments with large-scale landsliding. And if we use this little graphic here as a good example, where we start here on the left with the earthquake occurring, shaking's occurred, and that's induced landslides on a big steep slope, might be a little bit unstable. Landslide comes down, blocks a river. River banks up behind it, and we have what is called a quake lake forms. And eventually that river will build up, or that lake will build up, and eventually it'll either cut through that landslide or, and hopefully not, but potentially catastrophically break out. And we have what we call a dam break flood. These, of course, are potentially very, very hazardous to life. So this sort of cascading series of hazards is one of those things that we're really quite concerned about with an Alpine fault earthquake, where much of the Southern Alps and our mountainous terrain is likely to be affected by that. Now let's think about what's exposed. So I'm going to focus in on our critical lifelines, or our critical infrastructure, things like our power and road access and communications. So in the South Island, we have this beautiful, big, long, skinny island, which of course is very beautiful, a lot of tourist benefit, and a wonderful place to live. I've lived here almost my whole life. Absolutely love it. But it makes it tricky when we're trying to put our critical lifelines across it. Because with our long, big, skinny island, it's quite hard to have redundant networks across. So our state highways, for example, which of course are critical for general access, for our tourism industry, for goods and services moving around, such as our dairy industry or farming, mining, really important for moving goods and as part of that economic heart. Big, long, skinny network, as you can see here on this map. And what you're seeing with the image that's been displayed is the fatter lines are the number of vehicle routes that we're seeing. And this is data from 2013, so it's a little bit dated. And you can see that there's a lot of importance on that State Highway 1 with the route between Christchurch and Picton. At the moment, that's not quite open given the impacts of the Kaikoura earthquake. But it gives you a sense of what the usage, particularly from a touristic perspective, across that state highway network across the South Island. The other thing we need to be thinking about, of course, is electricity. So much of the New Zealand's generation capacity, especially from hydroelectric power, is down in the southern part of New Zealand, and usually a strong need to move that electricity north for where most of the consumers are. The problem with our networks is there's very little redundancy. So our long, skinny island means that many of our critical infrastructure networks pass through steep, landslide-prone terrain, especially when we're trying to get access to the west coast, with our Alpine passes being particularly prone to landsliding. You can imagine what that might potentially mean in a future Alpine fault earthquake. So the loss or potential loss of roads and power is likely to hinder our initial emergency response, but also potentially a long-term recovery of some of these regions. When we're thinking about Canterbury, we've got our western parts of Canterbury, of course, are quite mountainous, and so some of our more western parts of that region may experience challenges with this, so with a little bit of potential isolation and lack of access. Whereas much of the central and eastern parts of Canterbury are more perhaps resilient, or have a slightly better situation where we have a nice big flat grid-like electrical and road network, which perhaps provides a little bit more flexibility. So important to think about that in mind of where you are in Canterbury with respect to this. Now there's so many lessons about this from the 2016 Kaikoura earthquake sequence, where we saw how reliant we are on these critical lifelines, So the blockage of rail and road networks through that coastal area, but also the inland areas, causing large challenges. And so some of the lessons that we can take from that Kaikoura earthquake sequence around how we might estimate what are the likely impacts to us as people, the building damage and their loss of function, the social and economic impacts. And so there's a huge amount of work actively underway by both practitioners and researchers trying to make the most of what has happened, what can we take from this that was good, bad and ugly, and move forward with it to hopefully prepare for future events such as an Alpine fault earthquake. The next thing to consider is our electricity infrastructure. So out here on the right-hand side, there's a similar map where we're looking at the major or the high voltage transmission circuits or the power lines that move forward. So there's big pylons that you can see here down in the bottom left image. So much of our generation in the South Island is down in the southern lakes and southern river systems such as the Waitaki River, and much of that electricity is moved forward north towards the big users such as in Christchurch and further north into the North Island. Again, big, long, skinny network with some quite isolated or vulnerable feeds across to the west coast and so on. Now, the challenge that we have with our electricity infrastructure is, of course, with the landsliding that we forecast to occur, there may be damage to some of the pylons and poles. But the big challenge that's probably been forecast through this AF8 process and previous disaster planning prior to this is that these big hydroelectric power dams will shut down when they experience a large shake. And the reason for that is safety. They want to ensure that those dams are still secure and safe to operate and going to hold that big volume of water back. You can see the image here of Benmore Dam. And the challenge with that is that that'll immediately lead to a loss of generation capacity for New Zealand. So depending on how the rest of the New Zealand electricity generation system is looking, it may lead to brownouts or even blackouts in some areas in New Zealand and likely in the South Island. The additional challenge that we have here is that many of those dams actually require quite a lot of electricity to start back up. So if there's been a disruption of some of the dams between dams which can start back up again by themselves or even just being able to get electricity into those dams, it may be a challenge to get those things restarted. So in a big region-wide event like an Alpine fault earthquake, that becomes a concern. So there's a lot of thinking going into that by our electricity companies and the government agencies which are involved in that. But it's something to keep in mind that even if much of our electricity transmission and distribution network remains relatively unscathed from an event like this, we still need juice going into the system, or we need power coming in, and that may not necessarily occur. So important to keep in mind we may have electricity disruption through this. The final point about this slide is, of course, the importance of the Cook Strait cable, where it's the bridge between where we share electricity either with the North Island or the South Island get electricity coming back across. Remember that video of the ground motion simulation of that big energy wavefront moving north? There's a Transpower who operates that cable has put a lot of work into ensuring that it's as robust as possible. But things happen in disasters. It's a tricky business, this disaster thing. And so if that's damaged, we have a really important vulnerability there. So Transpower is extremely aware of that and are putting a lot of work and an effort into it. But again, it's these things that happen in disasters that we don't always know how they're going to perform. So again, something just to keep in mind with our planning. Okay, so we talked a little bit about the damage that might occur. The other things which I think are important to keep in mind here is restoration of our critical infrastructure networks. So obviously, restoring power, road, telecommunications, water, wastewater access is going to be a priority across many areas which receive damage from an event like this. But the challenge that we might have with this, especially in those mountainous areas or areas close to the fault line, is that we're going to likely have a large number of aftershocks. Some of them will be very large, and continued landsliding or unstable land or the liquefaction damage which has occurred is going to make restoration a challenge at best. We've seen that play out in and around North Canterbury following the Kaikoura-Huranui earthquake restoration, which provides a really essential examples of this, of the challenges, of the costs and the difficulties of undertaking this work. What I think is very pleasing is it shows that what we're seeing playing out in North Canterbury shows that it's possible, and that we have some amazing engineers and scientists and others that are all working together collectively to make that happen. But when we're talking about an Alpine fault event, it may be potentially quite a lot larger. And so some difficult decisions are going to need to be made around where do we use our finite resources. Particularly emphasising the issue around ongoing aftershocks and potential ongoing landslides and things like that. Some areas may be quite dangerous for many, many months afterwards. And a key decision is going to be, is it safe to allow restoration crews to go back into some of those environments? And a good example of this perhaps is, and just thinking through the practicalities of replacing these sorts of things, is if we're thinking about a power transmission pylon, Transpower estimates it takes about 2 days to fully replace a transmission pylon that's fallen down. The first thing that's going to be needed is safe ground access. Being able to get it into a site is going to be key. Is there road access? Can we get helicopters there? Are there enough helicopters available? The next thing is that how many spare pylons do we have available? How quickly can we manufacture them? These resource limitations are part of that challenge of disaster recovery. So restoration of some of these critical assets may take much longer than we perhaps initially think. And all of those complex interdependencies, which us Cantabrians have all borne the brunt of and thought about a lot over the last 7 or so years, could play out again. So what I'm happy to say as a researcher is looking at all the practitioners that are thinking about these things actively and managing these things, I feel quite heartened by the capabilities that we have here. Okay, so to wrap this up, the take-home messages, very similar to what's been said before on the Alpine fault, but let's just cap over the major things. So there's evidence that there's been over 27 large earthquakes occurring regularly over the past 8,000 years on the Alpine fault. They seem to occur regularly, so it's very, very, very likely that we will have another earthquake on the Alpine fault in the future. We have a world-class data set informing what the frequency of those earthquakes seem to be occurring, and it's difficult to stress just how good that data set is that GNS and the scientists from GNS and other organisations has collected on that. It's absolutely superb. So we think there's around about a 30% likelihood of or probability of a large surface rupturing earthquake occurring in the next 50 years on the southern portion of the Alpine fault. Very high chance, or high chance at least, that the next earthquake will be a magnitude 8. Widespread secondary hazards from any earthquake on the Alpine fault are likely, and are likely to present both an immediate hazard and challenges, but also a long-term one, potentially months, years, decades. Those effects will extend across the South Island and well into the lower North Island. This will be a whole-of-nation issue. And so finally, preparation is key. We live in a very active, beautiful country, but it's knowing what forces that have shaped that country are really important. And with having a situation where we have such a good scientific understanding of how the Alpine fault is working, and what the potential, or how that potential earthquake might play out in the future, is a very fortuitous one, and so we must use that information usefully. So preparing for that next earthquake is a really important part of what we're hoping to do through this process with Project AF8, and along with the sort of long-term work that our civil defence and emergency management groups are undertaking. So for us as individuals, as families and as communities, we know that there's likely to be a very strong chance there would likely be a future Alpine fault earthquake, along with other disasters which might affect New Zealand. So your ability to prepare for this is really important, and there's a lot of easy steps that you can take here. So check out the advice that civil defence and emergency management can provide, but do take that action, do be prepared.